All right, so we're ready to start with the last section in chapter 6, 6.3, which is looking at the binomial model. So we're going to be able to find probabilities using the binomial model. All right, so the next slide, we look at the binomial probability model. So this can be useful in many situations where we have discrete numerical variables, right? So what we want to look for to know if we can use the binomial probability model is that we need a fixed number of trials, which we can denote by n. Only two outcomes are possible at each trial. So typically we say a success and a something that's not success, right? A failure, right? So then part 3, the probability p of a success is the same at each trial, and 4, the trials are independent, right? So let me go back one slide. So here I just wanted to note, so let me just grab some ink here. So so as I was saying, P is the probability of success, right? And there are only two options. So if I take 1 minus P, then I can find the failure, right? The probability of getting a failure. So a lot of times, a lot of textbooks use the variable Q to denote that, right? So Q is simply 1 minus P. Right, so just some side notes there. So here's an example. So suppose that you toss a coin 8 times and count the number of heads. Explain why this is an example of a binomial experiment, right? So if we go to the next slide, I have this spelled out, right? So remember, the first thing we want to check for is fixed, right? Is the number of trials fixed, which is n. And in this case, n is 8, right? It's fixed. We're flipping a coin 8 times. And then 2, we need each trial to only have 2 outcomes, which is true, right? We can get heads or tails. So then part 3, we want the, whoops, didn't mean to jump. We want the probability to be the same at each trial, right? And that's true, right? If I flip a coin at each trial, I'll have 1/2 a probability of getting a head, right? For example. And then 4, we want our trials to be independent, right? In other words, we don't want one trial to be able to affect another trial, which is true. This is independent, right? If I get an outcome of one toss, it has no effect on the outcome of any other toss, right? So these are independent. So here are some more examples. So looking at these situations and trying to identify, are they binomial or not binomial, right? So you'd want to go through that checklist to make sure everything is satisfied. So we have these examples. So if we go to the next slide, we actually have the example, and then if it's binomial or not binomial, right? So for number 1, if we want to record the ages of a group of 20 randomly selected statistics students, this would be not binomial, because each trial does not have only 2 possible outcomes, right? There are many different ages that we could get, so there's more than just 2 possible outcomes. So automatically, that one is not going to be binomial. The second example we looked at is, let's say we want to ask each partner of a married couple whether or not they exercise regularly. Well, this is going to be not binomial since the couple is married. The trials are not independent, right, of one another, right? Then lastly, part 3. So in other words, with number 2, since we have couples that are married, they can have an effect on each other, right? That's the key there. So number 3, let's say we ask a random sample of workers whether their annual salary is greater than $50,000. And this is considered binomial, right? Either your salary it's either yes or no, right? You're asking, is the annual salary greater than 50,000? So that would be a yes or no case. Right, so next I want to talk about the shape of a binomial distribution. So the shape of a binomial distribution depends on n and p, right? Where n is the number of trials and p is the probability of success, right, at each trial. So here is an example of a binomial distribution where n is 15 and p is equal to 0.3. So something else when talking about the shape that I want to point out is that we're going to have a symmetric binomial distribution if p is equal to 0.5, but also when n is very large, if p is close to 0 or 1, right? So even if that's true. In case the general rule of thumb, right, is the condition is that you want n times p to be bigger than 10, and you want n times q, which is 1 minus p, to be bigger than 10. Right? If this is satisfied, we can assume that our binomial distribution is symmetric, right? Is normal, right? So this is the condition. Right, so that's a general rule of thumb to use. So like here in this trial, if I take 100, so let me scroll down here. Right, so if I take 100 times 0.3, that gives me, what, 30? So that's bigger than 10, so we're good there. And then if I take n 100 times q, which would be 1 minus p, so that would be 0.7, right? That would be equal to 70, which is also bigger than 10. So in this case, that conditions are met where we can assume that this fits a normal distribution, right? Or very close, approximately normal. Right, so you can see as long as n is really large, that can happen, right? So finding binomial probabilities. So binomial probabilities can be found by hand using the binomial formula if n and x are relatively small, right? But it's not practical. It's really, it can take a long time to find it using the formula, and the formula can be a little complicating, right? So in most applications, technology is something that we might use to find binomial probabilities. Right, so here's an example finding binomial probabilities for one value of x. Right, so we want to focus on just one value of x, and then we'll look at, well, what happens if we want to find more than one value of x. So it says, according to a recent Pew poll, 47% of Americans say it is important to control gun ownership. In a random sample of 200 Americans, find the probability that exactly 90 Americans say it is important to control gun ownership. Right? So in other words, we're trying to find what's the probability that x is equal to 90, right? Exactly, it says exactly 90. So we want to find this. So first we want to check and make sure it's binomial, right? So do we have a fixed number of trials? Yes, we do, right? There's exactly 200 trials. We only want 2 outcomes for the trial, and yes, right? It's either yes or no, right? You either agree it's important to control gun ownership, or you don't, right? There's no gray area here, yes or no. 3, the probability of success remains the same for each trial. Yeah, right. The p is 0.47, and 4, trials are independent, and yes, they would be independent here, right? So some notation with this. So in this problem, we're looking for a binomial probability where n is 200, p is 0.47, and x is 90. So to denote this, we use this notation, right? So remember before with normal distributions, we used n, and then we did mu, right, the mean, and then standard deviation, right? So if we had n of 0, 1, right, that was a normal distribution. This tells me my my mean and my standard deviation, right? And those 2 things indicated what type of shape we were looking at. Where with the binomial distribution, we're concerned with n, p, and x, right? So this is just another way to denote that, right? So taking this information, we can denote it with this, right? So we can do this using the graphing calculator, or I'm also going to show you how to do this finding R. Right? So first of all, we're looking at how to find a single value of x, the probability for a single value of x. So to do this, we're going to go to second distribution, and in this case, we want the binomial PDF. Right? So to find this in the TI, right, we're going to take binomial PDF, and then we're going to put in 200, 0.47, and 90. Right? So let me open up my graphing calculator. Right, so first of all, we need it on. Right, go to second distribution, and then we want binomial PDF, which is this one, right? Option A, binomial PDF. So hit enter. So we're going to type in the number of trials. So there were, 200 trials. So type in 200. Then we're typing in the p-value, which is 0.47. Oops, didn't get the 4 in there. 47. And then the x value is 90 that we want to look at. I hit enter, paste, enter again, and there's my probability, right? So the probability of getting exactly 90 is roughly 0.048, right? So roughly about 5%. Right? So that's how you would do this, finding this using the graphing calculator. Now using R, we use this command, and I'm going to type in X and P, right? So it's in a little different order, but it would be the same thing. Right, so let me just make note here, right? So in R, we're going to do the command D binomial. We're going to do X, N, and then P. Right, so in this case, let's see, X was 90. N is 200, and P is 0.47, right, in our example. So now I can pull up R. Let me make the font bigger. Right, so we'll just type this command in, right? So it's D binomial, then type in X, which is 90, comma N 200, comma 0.47. Right, and we get the same probability, right? Roughly about 5%. So not too bad, right? So we looked at finding just one value of x, but what if we want to find probability for more than one value of x? So here's the example. According to the Bureau of Labor Statistics, the unemployment rate in Detroit in June 2014 was 10.2%. If a random sample of 15 people living in Detroit at the same time was taken, find the probability that 3 or fewer were unemployed. Right, so again, check to make sure it's binomial. So do we have a fixed number of trials? Yes, right? N is 15. Number 2, are there only 2 outcomes? Yes, right? It's yes or no. 3, the probability of success is the same for each trial. Yes, right? That is 0.102. And my trials are independent, right? So we have all those conditions met. So then now when we think about when we have 3 or fewer, right? That includes 3 and goes all the way down to 0. So in other words, x could be 0, 1, 2, or 3, right, as listed here. So we need to compute the following. We need to compute the probability with a binomial distribution that x is 0, 1, 2, 3, and 4, and add them up, right? So that process can get very lengthy to have to add all those up together. So you can certainly do that using the methodology we used before in R and also in the TI, and then just calculating each one of those and then adding them up. Or there's a quicker way. There's a command that will do 0 to 3 for us, right, automatically. So instead of computing 4 binomial probabilities separately and then adding them together, we can take advantage of the probability cumulative density functions built into certain technologies. So this will add up 0 to whatever x value we want to specify, right? So using the TI, this is the command that we're going to put in, right? So in this case, right, we want to find the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 plus probability that x is 3, right? So instead of doing all of these separately, we're going to use, in the TI, use this command. So it's binom CDF, and then we're going to put in your n value, so n, and then p, and then x, right? So in this case, n was 15, right? So n is 15. P is 0.102, and for here, when I'm putting x, I think of this is the largest x value, right? So the largest x value we want, the largest x, is 3. Right? So I'll grab a graphing calculator. So we'll go to second and then distribution, right? So second distribution. Oops. There we go. Second distribution. Then we go to binom CDF. So we want to scroll down, which is B, option B, right? So hit enter. So the number of trials, right, that we have are 15, right? We're doing 15 trials. My p value is 0.102, and my largest x value is 3. All right, so I hit paste, enter, and we get 0.941 roughly, right? So we can find that all together. Right. So you can think of this as the largest x value that you want to go to, or it's finding the area to the left, right? So we have like this normal, we have this distribution. Here's x equals 3. It wants to find all the area to the left, where here x is 0, right? That's always going to be your tail. So you can kind of think of it like that too, if you'd like. Right? So I like to think of it as the largest x and then going down to 0. So in R, I'll show you how to do that. So in R, you're going to use the p binom command, right? So you use p binom, and then we type in x, and then n, and then p, right? So let me pull up R again. Right, so to find this, we would type in p binom, and then the largest x value is 3, and then n is 15, and then p is 0.102. And then we get the 94 as in the graphic calculator, right? So if we compare, we get the same, right? So something in this section that you want to be careful with is language, right? So for example, if we have more than 5, right, this does not include 5. This means 6, 7, 8, all the way to n, right? All the way to the largest trial. Where if we say 5 or more, that includes 5 now, right? So there is a difference in this, right? In this language. So before, we didn't have to worry about this because the probability of getting 5 or more is the same as the probability of getting more than 5, right? That turns out to be the same, right? So with binomial distributions, we do need to worry about this language. So here's some practice identifying x values. So what x values are implied in each of these phrases, right? So more than 6, fewer than 5, and so forth. So more than 5, or excuse me, more than 6 means that we want to start at 7 and go all the way up to n, right? Where n is the number of trials, right? Number 2 is we want fewer than 5. So fewer than 5 does not include 5, but goes 0 all the way to 4, right? Number 3, if we say at least 7, right, that includes 7 and goes all the way up to n. And then if we say something like between 3 and 7 inclusive, right, that means that inclusive means that we're including 3 and 7 both, right? So that would be 3, 4, 5, 6, and 7. And then if we say 10 or more, that's 10 all the way up to n, right? So you want to be familiar with this language and know what that means, right? So here's an example. So this has to do with medical coverage. So according to a report in the Sacramento Bee, only 11% of Californians lacked medical insurance after the passage of the Affordable Care Act, down from a previous rate of 17%. Suppose a random sample of 80 Californians were taken after the passage of the Affordable Care Act. Find the probability that A, more than 15 lack medical insurance, and B, between 10 and 20 inclusive, lack medical insurance, right? So let's take some notes. Right, so I would just take some notes off to the side. So n is 80, p is 0.11, and if I want to find the probability that that more than 15, right? In other words, x is bigger than 15. This would be finding when letting x be 16, 17, all the way up to n, which is 80, right? So we want to find all of those. Right, so I want to find the probability that x is greater than 15. So with this, they already found that the probability that x is greater than 15 is equal to 0.013. Right, so this is a printout of StatCrunch, which is a software that comes with Pearson, but I don't think is so practical because it's not really used in practice, right? So that's why I want to teach you how to use R to find this. So if we wanted to find this using R, right, we'd have to think about what command that we want, right? So we can think about this as like an area, right? Trying to relate it to what we did earlier with the area of the bell curves, right? So here's 15. So here's 15 all the way to 0, right? So we could use R to find this, but we want to know what's bigger than 15, so 16 all the way to 80, right? So what we could do is both of these add up to 1, so I could take 1 minus and then find, well, what's the probability that x is less than or equal to 15, right? So we could calculate that using R, certainly, right? So if we go, if you go to previous slide, right? Some previous slides, I told you how to do this in R. Oops, I went too far. Right, so in R, right, we want to use the p binom command, right? So p binom, and you put the largest x, the n, and then the p. Right? So if I want to find that area, I can do this using R. And again, just to point this out, if I use the command, so if I use the command p binom and then 15 comma and then n was what, I think 200? No. N was 80, right? So I would type in 80. And then my p-value, which is 0.11. Right? So if I type in the command just like this, what this is finding is what's the probability of 0 plus probability of 1 plus probability of 2 plus probability 3, 4, all the way up to 15. Right? But I want to know 16 to 80. But I know that both of those add up to 1. So if I find this and take 1 minus that, hit enter, that will give me the probability of 16 plus 17 all the way up to 80, right? So we get 0.012. Right, so if we look at go back to where we were on the PowerPoint, right, that's just rounded, right? So they rounded to 3 decimal places to 0.013, which is perfectly fine. Right? So you want to be comfortable, right? So remember, so R always goes down. We want it to go up, right? So pay attention to how we would enter that in. So if we want to go between 10 and 20, right, we can do something very similar in R, right? Or you can do this in the graphing calculator, right? Whichever you prefer. So if we want to go in between 10 and 20, so I want to know the probability of 10 plus probability of 11 plus all the way to probability of 20. Right? Then doing this in R, we're going to have to do some subtracting again, right? But instead of doing this one in R, right, since we've done that a couple of times, I want to use the graphing calculator this time, right? So if we go back to how to do this in the graphing calculator, we use the binom CDF command, right? We put in, first we put in n, and then we put in the p-value, and then you put in your x, right? So it's very similar philosophy, just how you enter it in the computer is a little different, right? So we have to think about, how do I find this, right? So let me make this a little larger here. So this is what I want. Right? So if I enter the command binom CDF into my graphing calculator, and I type in, so my n was, what was it? N is 80. Let me just rewrite my notes here. So n is 80. P is, was it 0.11, right? 11%, I believe. Yes, right? So if I type this in my calculator, binom, and I went, so we want to go all the way to 20. Right, so if I did binom CDF 20, comma, and then I did so next we do P and then X, right? So excuse me, this should be 80 and then P 0.11, and then do my X, my largest X is 20. Next, we want to find in between 10 and 20. Think about what this does. This gives me probability of 0 plus probability of 1 plus probability of 2 all the way to we get the probability of 20, right? So that's okay. But I want to get rid of everything that's probability of 0 all the way up to probability of 9, right? This is what I want to subtract off. So I want to subtract this off. So what I could do is take the binom CDF of, so this would be 80, 0.11, and then this would be comma 9, right? So now if I take this entry minus this entry, then I will arrive at what I want, right? This will leave me with probability of 10, right, plus probability of 11, plus all the way to probability of 20, right, which is what I want. Right, so you have to think through how to enter this in. So using the graphing calculator, right, I would go to second distribution, and then we want the binom CDF. Right, option B. So the number of trials are 80. The p-value is 0.11. The x value for the first one is 20. And paste, right? And then I want to do minus, and then do second distribution. And then we want option B again. Binom CDF. We want 80 trials. 0.11. Now my x value now is 9, right? Enter, paste, hit enter, and we get 0.38, right? 0.3844, which is exactly what we get here, right? In this printout on this slide, right? So that's how you could do that in your calculator. If you want to do this in R, it'd be a very similar setup, right? So let me adjust the screen here. So we're doing this in R. We would want to take P binom, right? And then we want to hit in 20, right? The x value, comma, and then we're doing 80 trials, 0.11 was our P value, and then you would do minus, and then P binom, and now the x value we want to go to is 9. And then 80 trials 0.11, right, as my p-value. Hit enter, and we still get the same value, 0.3844, right? So same result. So that's how you can do that in the graphing calculator R, but the hard part is thinking this through, right? All right. So the mean of a binomial distribution, right, this is sometimes called the expected value. And this can be thought of as the number of successes we would expect if the experiment were repeated n times, right? So as with distributions, this tells us where the distribution balances, right? So the formula to find the mean is you take n times p, right? The number of trials times the probability of success. So let's practice finding the mean. So suppose you toss a fair coin 15 times and count the number of heads. Find and interpret the mean of the probability distribution. So the mean would be 15 coins, and p here is 0.5, right? Because I have a 50% probability of getting a heads. So 15 times 0.5 is 7.5. So, and we can't get exactly 7.5 tosses, right, to be heads. But if I toss 15 coins, I would expect to get between 7 and 8 heads, right, with 15 tosses, because again, we can't get 7.5, so we would expect to get somewhere in between 7 and 8, right, roughly. So here's a mean of a binomial experiment, what it looks like on the graph, right? So the mean represents the balancing point of the distribution still. So also we can talk about how to measure the spread, right? The standard deviation. So the formula is sigma is equal to the square root of n times p times 1 minus p, right? And just a note, so I told you before that when I have well, let me get some blank space. So when I have 1 minus p, this can also be represented as q, right? So if you wanted to, you could say sigma equals the square root of n times p times q, instead of what's written here. It's just a preference, right? So our book uses 1 minus p, but a lot of people also use this variable q to represent the failure. So this can help us approximate a range of values. We would expect a range of values we would find surprising in a binomial distribution, right? So here's an example of standard deviation. During his career, Major League Baseball player Buster Posey of the San Francisco Giants has a batting average of .308. This means that he gets a hit about 30.8% of the time when he bats, right? So that's just making sure you know what a batting average means, right? So if he bats 480 times in a season, we would expect him to give or take how many hits, right? So that's one question. And then, so the expected value is the mean, right? So remember, the mean, or the expected value, is finding n times p. So n is 480 times, and p would be his batting average, right? .308. Right, so this would tell me my expected value. This is what I would expect to happen. Right, and then we're also asking, is it unusual if you got 120 hits? So is this unusual? Let's find out. So here, for the expected value, right, like as I was saying, we want to find mean, which is n times p. So that would be 480 times .308, and we get 147.8. So this is the expected value. The standard deviation, right, we find by taking the square root of n times p times q, or n times p times 1 minus p, right? So if you do this, you get 10.1, right? So we expect Posey to get within one standard deviation of the mean, right? That's 68%, right? Using the empirical rule, 68% of our data would be in between that. So that's what we would expect. So if we take one standard deviation away and add one standard deviation, we get a range between 137 to 157.9 hits, right? So then, continuing on with, would this be unusual, right? So one way we could find out is it unusual is we could find a z-score. Oops, didn't mean to go. So we know that 120 is beyond one standard deviation below the mean. So determine if this would be so surprising, right? So remember 68, 95, 99.7 rule, right? So remember, within z, so within one, right, we have 68% of my data. Within two standard deviations, right? So this is just the empirical rule. We have 95% of my data. And then within three standard deviations, we have almost all the data, right, or 99.7%, right, roughly. So what we're trying to do is figure out, well, how many standard deviations away from the mean am I? So that's what a z-score tells me. So remember, to find the z, right, we would take the value we're considering, 120, subtract off the mean, which we found to be 147.8, right, the expected value, and then divide by the standard deviation, which we found to be 10.1. So if we do this, we get negative 2.75. So is this surprising? Yes, right? We would say that's very, very unlikely, right? So to put it in context, right? So if here is negative 2 z-score and here's a positive 2 z-score, right, we would expect 95% of my data to be in between here. But this score is even further to the left, right, negative 2.75. So even further to the left makes it surprising. So this would be surprising, right? It's much lower than we would expect out of this particular batter, right? All right, so that's the end of this section, right? So as always, if you have questions, make sure you contact me. Thanks. Bye.